Okay, so today we're starting 2-7 tangents and derivatives. So for circles, a line L is tangent to a circle at a point P if L passes through P perpendicular to the radius at P. These lines just touch the circle. So, if I have a line L that's touching the circle, then it has to be perpendicular to the radius at this point. So I have the perpendicular sign here, showing that it's perpendicular to this radius OP from the origin of the circle out to P. A line that's tangent to that just touches the circle directly at that point P. Now, this point P can be anywhere on the circle. So right now I have it just touching at the point P. My line goes through that point and touches the circle directly there, but nowhere else. And we've learned about tangents before. We've seen the way that they work. Additionally, I could put P anywhere on my circle, say there. And then if I draw the radius out to it, I would then draw a line perpendicular to that radius that goes through that point and is only touching the circle at directly this point. And so that's how you find a tangent. Tangents to a curve are not as easy to define because depending on the shape of the curve, the tangent line might go through the curve more than once. So if I look at this curve, my line L is a tangent at the point P right here, but it also goes through the curve here. Unfortunately, all that can really do is confuse us. Just look at the point where I'm trying to make it tangent to. So just think about it that way. Don't worry about the point where it crosses through it. Obviously, that has nothing to do with a tangent, which is just touching the curve and kind of bouncing off. So if we're looking at the point P, that's what we're concerned with. To define tangency for general curves, we need to take a dynamic approach that takes into account the behavior of the secants through P and the nearby points Q as Q moves towards P along this curve. This figure is going to come next, so at least just write this down so that you can figure out what is happening here. So we start with what we can calculate. Namely, we can find the slope of the secant between P and Q. Then if we look at the limit of the secant slope as Q approaches P along the curve, as I move my point closer to P along the curve. So if I'm looking at the limit of that, if the limit exists, then we can say that that is the slope of the curve at P, and define the tangent to the curve at P to be the line through P with this slope. All right, well, that's a lot of fun to figure out. I'm going to show you exactly what that means here. If I'm looking at a tangent of the curve at the point P, right? Then I'm looking for, as it touches this curve, what does my line look like directly going through that point? Now, it's hard to figure out exactly what my slope of that would be, because is it this? Is it this? And so what we find is that we can take the secant, which is P and Q. Now I have 2 points, right? And if I start with this, and if I'm trying to find the tangent or the slope of the tangent line at P, then if I have this point Q, I could pick out a number here and say P is the origin, 0, 0. And Q is, say, 4, 2. Then I can use my slope formula to find that, right? But the problem with the tangent line is that we don't know what other point this would be going through in order to use the slope formula. doing like 2 minus 0 over 4 minus 0. So you can't use a slope formula for that because I'm only going through one point. So if I'm looking at the tangent at P, then the tangent of this looks to be about that. That's just touching directly at that point P, nowhere else on the arch or on the curve anywhere. And so I'm looking at a line that kind of looks like that. Would PQ be a good approximation of my slope? It doesn't look very good, simply because this one goes out much further than this one, right? So this one's not as steep as this line here, which I'm assuming is close to my tangent. Everything that we learned in the last, this little paragraph here, says that if I move Q towards P, then by doing that, I can get closer and closer to what my slope of the tangent line actually is. So the closer and closer that Q gets to P, the closer and closer my line of the secant between the two, or my slope of the secant between the two, gets to my actual tangent line. And so everything we've done in this section so far talks about limits, right? And so this is actually an approach for a limit problem. As my Q gets closer and closer, my secant line gets closer and closer to what the tangent is. And so if the limit exists at P, then I can get Q close enough that I can just find the limit at the point P of the curve, which would give me my tangent line. In other words, we can find the definition of the slope in the tangent line. The slope of the curve y equals f of x at the point where we just have some random x we plug in and find a y, is the number m equals, the limit is h approaches 0 of f of x naught plus h minus f of x naught over h. In other words, for this, what we're saying is that h is our gap between P and Q along the x. So as I get closer and closer to P, or my x naught, then I can plug that number in, plus my gap to the formula, minus just plugging the number in and dividing by h, and you're taking the limit as h approaches 0. This is just the way that we define this. So make sure that you write this down so that you have a good example to look off of as we move into the examples here. The tangent line to the curve at P is the line that's through P with this slope. So now we can find a tangent line based on finding this limit. Finding the tangent to the curve, this is our formula for doing this. So the first thing that we do is we calculate f of x naught. So you plug x naught, or whatever your point is, your x value of P, into the equation. Then you find f of x naught plus h, or the gap between the 2 points. Calculate the slope based on our last definition. And if that limit exists, then we find the tangent line as our y naught, or just this value of point P, plus m times x minus x naught. So this is our process for finding the tangent to the curve. Oops. So now we're going to walk through some examples here. Slope and tangent to y equals 1 over x, where x is not equal to 0. And then it says, what is the tangent line at x equals 4? So basically we need to start by plugging in this point x equals 4 so that we can find our f of x naught. So we plug in f of 4 into this equation. That gives us 1 over 4. Now we don't know what our distance h is, so whenever we plug that in, we just plug that in as 4 plus h. And so that gives me 1 over 4 plus h. And so we have step 1 done of what we were trying to do here. We found f of x naught and f of x naught plus h. Now we're going to calculate our slope using this portion. So to calculate our slope, it's the limit as h approaches 0 of f of x naught plus h minus f of x naught over h. We plug in our two values here. This is f of 4 plus h. It goes in for x naught plus h. And f of 4 goes in for f of x naught. So it's the limit as h approaches 0 of 1 over 4 plus h minus 1 over 4 all over h. Now before I can subtract these, I have to get a common denominator here. And I can't just add h to this one because, well, it's not mathematically allowed. So I have to multiply this one by 4 on top and bottom, and multiply this one by 4 plus h. That's the limit as h approaches 0 of 4 over 4 times 4 plus h minus 4 plus h over 4 times 4 plus h. And that's all over h still. Now I can combine these two because they have the same denominator. And distribute my negative to both of those terms. So that's 4 minus h over, and I can distribute my 4 down here. Gives me 16 plus 4h all over h still. Four minus 4 gives me 0. Those cancel each other out. I'm left with negative h over 16 plus 4h all over h. This is a compound fraction, so remember we just make our h over 1, flip it and multiply. Gives you the limit as h approaches 0 of negative h over 16 plus 4h times 1 over h. Now my h is going to cancel with that one. I'm left with the limit as h approaches 0 of negative 1 over 16 plus 4h. I can plug my 0 in for h. That makes this back term 0. And my slope is negative 1/16. So now I found my slope of the tangent line. But I'm not done yet. I still have to plug in y naught and our x minus x naught. So this is y equals y naught, which our y naught is what we found when we plugged the 4 in, so 1/4. And then that's plus our slope, so it's really minus 1/16. Times x minus x naught, which was 4. And that all just came from this step here. Now multiply this out. That gives us y equals 1/4 minus 1/16 x minus 1/4. Those cancel each other out. And I have y equals negative 1/16 x. And that's the equation of my tangent line. Now, if I wanted to see how true that was, I can graph it. I'll just graph my equation 1 over x, which was the original. And then we got y equals negative 1/16 x. And that gives me my tangent line there. There's something wrong here. It's not quite right. I need to have that negative 1/16 x plus 1/4. Let me see what our problem is here. Oh, rookie mistake. That's a real rookie move. I'm embarrassed right now. I'm embarrassed that I just erased all that too. Negative 1/16 has to distribute to both of those. So it wouldn't have been 1/4 minus 1/4. It would be a plus 1/4. So 1/4 plus 1/4 is 1/2. Our actual equation is negative 1/16 x plus 1/2. And I'll show you how I knew that I messed up there. When it was just negative 1/16 x, my line at 4 should be touching my curve here. But it wasn't touching the curve. So it should just be touching, my blue line should be touching and not going through the curve, but just touching directly at that point. When I saw that it wasn't, I knew I had to fix something. Now, if I look at 4, both are exactly there. As a matter of fact, they're so close, you can't even see the blue line anymore, or the red, depending on which one it gets rid of. And so that's how you know it's tangent to the curve at that point. It's touching directly on that point, and there's no gap in between the two. All right, we will definitely do a lot more examples of these on Monday when you guys are all back in school. Hooray. Actually, I think only one person's here on Monday. That's nice.